These figures are from a review article on the topic of non-line of sight imaging by Fazio, Belton, and Wettstein. Non-line of sight imaging consists of using remote scatter to image an object rather than the field directly scattered by the object. Here we assume that a laser signal comes and illuminates the scatter, and then that signal illuminates the object after it's reflected by the scatter, and then the field hitting the object is rescattered and then illuminates the wall here. And by imaging the scattered field from the object, one hopes to reconstruct the object itself. This can be done by various methods, as we'll discuss in today's video. One approach is to measure the time delay from the original signal hitting the wall back to the wall on the scatter, and by measuring the time at a diversity of points, one can tomographically reconstruct the object itself. And what's shown here is various algorithms using the same data to reconstruct the object from this scatter field. We'll talk about how this works in today's video. Computational imaging. Episode 33, Scatter Imaging. As discussed in the introduction, our goal is to consider how to reconstruct an object which we don't observe directly from its scattered field. So we assume that illumination strikes the scatterer and then illuminates the object, and then the scattered field returns to the scatterer. Now, if we did this with ray optics, we would have to have a coated aperture or some kind of optical component that could structure the scatters in a way that we could reconstruct it. But in the case of wave field imaging, we can hope to reconstruct the wave field on the surface of the scatter and then reconstruct the object by backpropagating the wave field. Now, this is going to be somewhat challenging because, of course, the scatter is diffuse and will scramble the phase of the wave field incident on it. Of course, if the scatter was a simple mirror, then we can just see around the corner directly. But because the scatter is diffuse, the phase information of the wave field is nominally lost, so we need to come up with some method to recover the phase of the wave field on the scatter and backpropagate and reconstruct the object. Today's episode discusses three mechanisms by which we can recover the wave field on the scatterer and then image the object. The first approach uses pulsed illumination. So the illumination is a pulse P of t, propagates to the scatterer, then propagates from the scatterer to the object, and then is reflected by the object, which we've described here as f of r, and then is time delayed coming back to the object. And based on where on the scatter the signal returns and the overall time delay, we observe a time delayed signal hitting the scatter from each point on the object, with the time delay proportional to the overall path length to that point on the object. So here we're assuming effectively that each point in the object is generating a spherical wave in proportion to its illumination. Now, we've seen already that we could analyze this system in frequency space, temporal frequency space, instead of time. And so we had this form for each point in the object generates a spherical wave according to the Green's function. And in diffraction tomography, we analyze this to reconstruct the three-dimensional form of the object by observing the object from a variety of directions. We have the problem here, though, that we do not observe this scattered wavefront. Instead, we observe the intensity, the magnitude squared of the wavefront after it's been modulated by this T of x, which is the amplitude and phase modulation associated with the scatter screen. So we somehow have to solve this phase retrieval problem to get g of x and nu in order to apply the same diffraction tomography techniques that we used in the last couple episodes to reconstruct the remote object. So this has been done in a variety of different ways. One of the popular ones in this field of non-line of sight imaging is to illuminate in the time domain instead of frequency domain. Now, as we've already seen, time domain illumination has problems with SNR, but it has the advantage that there's a known phase relationship between all of the frequency components of the signal. And so you can use the fact that you know the temporal signature of the wavefront to effectively implement phase retrieval and recover the signal. In typical non-line of sight systems, this is done by simply assuming that the scatter is non-negative and that the measurement of the scattered field is an intensity measurement, in which case one assumes that it's a ballistic photon kind of situation, and effectively we're assuming that the magnitude squared of the field is equal to is proportional to the field itself. And if we make this assumption, then effectively we're measuring a time delay along each possible propagation direction of the field. This technique is particularly appropriate when the object is not actually three-dimensional, but consists only of a range bin for each scatter point. And when that is the case, then these kind of back projection algorithms that were shown on our introductory slide could be used to reconstruct the object. The resolution in this case is going to be proportional to the temporal width of the signal, because basically we're using the pulse to measure time delay at various points on the object. So if, for example, we had a nanosecond pulse, then you'd have about a 25 centimeter, a quarter meter kind of spatial resolution. If you go down to a picosecond pulse, you could get down to a millimeter scale resolution. But you're limited by this overall time delay, and you're limited in the complexity of the object because you've essentially made this assumption that the object is a positive valued scatterer. That's solution number one, to how do we reconstruct the wavefront on this remote scatterer in a way that allows us to image the remote object. Another approach has been holographic, in keeping with the holographic techniques we've already studied in this chapter. This is synthetic wavelength holography. It allows us to cancel the phase distortion caused by the scatterer. This is work by Willemser and et al., as described in this work in Nature Communications in 2021. Here we illuminate with the laser source, and so here's the hidden object illuminated with the source hitting the scatter, but we interfere the scattered field from the object with the reference wave. And so now by looking at the reference wave and the latent field, we are able to reconstruct the wavefront on the surface of the scatter. The problem that we face, however, is that this wavefront on the surface of the scatter is modulated by the complex valued random modulation of the scatter itself. So somehow we need to find a way to cancel out the effect of the scatter in order to be able to reconstruct the object. This technique, if we can cancel the scatter, could be used for this non-line of sight geometry where the scatter hits back onto a phase screen. It could also be used to image through scatter if the scatter is in the path of the observation of the camera rather than just a phase screen. To do this, we assume that the phase of the scatter is the same at two different frequencies. So we assume that we're going to capture the hologram on the surface of the scatter at frequency nu1 and frequency nu2, and these frequencies are close enough to each other that the modulation due to the scatter is equal at those two frequencies. And so we're measuring the magnitude squared of the signal at each of the two frequencies. Each is modulated by the distortion from the scatter. When we multiply this out, we have the field magnitude squared at frequency 1, the field magnitude squared at frequency 2, and this cross term. We could isolate the cross term by spectral filtering. If there's a beat frequency between the two frequencies, we can filter on that. It's also possible just to measure the hologram at the two different frequencies and then digitally multiply the holograms together to cancel out the scatter field. So if we assume that we're able to measure this term g at lambda 1 times g at lambda 2, then the field at each one of the frequencies is the field due to the remote scatter propagated from the scatter to the screen. So this is the propagation kernel from the scatter to the screen. Now, if we assume that the scatter itself is a diffuse scatter so that it's delta correlated, then we'll assume that the expectation value of the product of the field scatter from two different points on the object has this delta correlation. That allows us to reduce this double integral to a single integral, where now the correlation between the field at lambda 1 and the field at lambda 2 is the intensity from the surface of the remote object propagated with this kernel. This kernel operates at the synthetic wavelength. So when we take this 1 over lambda 1 minus 1 over lambda 2, we generate a synthetic wavelength, which is the geometric mean of lambda 1 and lambda 2. So in the GitHub repository that goes with these episodes, there's a notebook that implements a simple example of synthetic wavelength holography. So you can go look at that notebook, and there you see we have the field of image 1 and the field of image 2 in the system. And now these are at two different ranges. We have two different objects, one at range D1 and one at range D2, and we'll capture the field from those two objects in the field Q1 and the field Q2 at two different wavelengths, lambda 1 and lambda 2. And now it happens in this simulation that lambda 1 is 1 micron and lambda 2 is 1.05 microns. So the difference in the two fields wavelengths is 50 nanometers. And then we'll measure this conjugate, and we assume that we measure the field due to one of the one hologram times the conjugate of the field due to the other hologram. And so we've now captured a holographic signal at the synthetic wavelength of the two fields, and we don't include the phase screen here because the magnitude of the phase screen we assume would cancel out when we multiply the field at lambda 1 times the conjugate of the field at lambda 2. In this simulation, this is the absolute value of the synthetic hologram. The objects that we're looking at are assumed to be about 2 millimeters high, and in the simulation they consist of digits 2 and 4. One of them is at a range of 4 centimeters from the scatterer, and the other is a range of 6 centimeters. It doesn't really matter how far the observation is away from the scatter, as long as we have enough spatial resolution to reconstruct this hologram. So we'd have to analyze the spatial resolution that we need. Here the hologram is somewhere around a centimeter on a side, and we would need somewhere around 100 micron-ish sort of resolution on that to be able to reconstruct these objects at the ranges shown here. But of course, different geometries will have different resolution requirements. Now, when we backpropagate the signal, we've assumed that these scatterers are diffuse scatterers, and so they create a broadband signal that we see in the recorded hologram because the objects have a random phase at each point. When we backpropagate, we have the problem that we see, of course, the reconstructed signal, but we also have the diffuse background from the other terms. And so we could, of course, use these decompressive inference techniques that we talked about in a previous episode to try to reconstruct the three-dimensional object itself rather than the object with the background. Exactly at the synthetic wavelength, exactly the kind of decompressive holographic techniques that we talked about earlier could be applied. So that's method 2. We've first of all said we could use pulse illumination to have a time-gated version to measure propagation time delays in the signal coming to the scatterer and use that to try to reconstruct the image of the object from its scatter. We've seen that we could create a synthetic hologram comparing the holographic data at two different wavelengths to cancel out the phase effect of the scatter and do the reconstruction. The third method would be just to simply apply phase retrieval. So this is our solution number 3. We have the remote scatterer, and once again the scatterer is a diffuse phase screen. In this case, we're going to assume that we image the intensity. So the scatterer is effectively an intensity detector. So we measure the magnitude squared of the field on the scatterer by looking at it with the camera. So we're just going to image with a camera with a incoherent imaging system that takes a picture of what we see on the scatter. So the scatter is effectively acting like a remote camera. And we have the problem, though, that because we're looking at the magnitude squared of the field on the scatter, we've lost the phase of the signal on the scatter, which has the advantage of that the phase of the scatter itself doesn't really affect our signal, but has the disadvantage that we can't backpropagate the field without measuring its phase. So here in this situation, we have the source illuminating the object. We have the scattered field that we measure on the scatter plane, and we're interested in the distance between the camera and the object and the difference between the camera and the scatter plane, and those will all be important factors in determining the resolution with which we can reconstruct the object. Here's an example of an experimental system that implements this. The scatter, in this case, so here's the illumination source, and the object is somewhere in here, and then the scatter is measured on this sign. There's a white piece of paper on the sign that we're going to image, and then the observation camera is way down here. It turns out to be a quarter-meter telescope that we're observing the scatter from 100 meters away. Here's reconstructions that we can see. This is, in this case, the object is a resolution chart. If we directly observe the resolution chart with the telescope, well, we see this, and then this is a phase retrieval reconstruction of the object, which is far from perfect, but has features that are consistent with the structure of the object. This is a relatively complex object, which was challenging to reconstruct with phase retrieval. The interesting thing here is that the object size. So this is like 2 millimeters on a side, and the feature sizes that we're going to look at are on the 100 micron or smaller kind of scale. But the scatter that comes from the object, because the scatter is a couple meters away from the object, is going to be much larger. So the scatter is somewhere around 10 centimeters on a side. So we've taken this small object and increased its size actually to not 10 centimeters, but somewhere around a quarter meter on a side that we'll analyze to do the reconstruction. And for this relatively simple object that created that scatter, here's what a reconstruction looks like. So we have a set of bars on the object, and imaged at 100 meters, we can reconstruct these bar features down to something like a 14 micron resolution, which corresponds to 140 nanoradians with a relatively modest resolution telescope. So what we've done here is create a remote aperture, so that we have the aperture of the telescope here, but the telescope is some distance away, in this case 100 meters. And then we have the aperture of the scatter, which is the same aperture basically as the camera, somewhere around a quarter meter. But the scatter is much closer to the object, somewhere around a meter. So because of being, around 100 times closer, in this case about 50 times closer to the object, it's possible to get about 50 times higher resolution on the object than you would get with the camera itself. In this case, the camera resolution is somewhere in the millimeter range, and we're able to reconstruct somewhere in the range of 15 microns. The increase in resolution you can compare with what you'd get from the direct view. The resolution that we would see, the angular resolution you would see from the camera, is the wavelength divided by the camera aperture times the range. The angular resolution you get from the scatter is the wavelength divided by the aperture of the scatter, the size of the scatter on the screen, times the range to the scatter. And so the improvement in resolution should be the ratio of these two. And so if, of course, the scatter is much closer to the object than the camera, we'll get an increase in that factor. Now, for this particular case, the resolution on direct view is from the aperture of the telescope, and the range is around 235 microns. The resolution that you would expect from the range to the scatter would be 4 microns, which is better than the 14 microns that was actually achieved, but still the 14 microns is much less than the resolution you get from the direct view. The theoretical limit for this process of how much improvement in resolution you can get really depends on how big the aperture of the scatter can be, and that depends on the photon count that you get. How many photons do you need on the scatter in order to be able to resolve it and use it in your signal? So it turns out that the resolution enhancement you can get by imaging from the phase retrieval on the scatter signal is proportional to the the photon flux. This sigma is the efficiency with which the illumination is scattered. L is the illumination luminance. T is the time. So this basically is a measure of how much signal is reflected by the scatter. And so P is like a measure of how many photons do you need to be able to reconstruct a feature. This aperture of the camera and the range between the camera and the scatter is a measure of the efficiency with which the camera is going to be able to collect scattered light. and then this delta is the pixel pitch, and this is the diffraction limited pixel pitch for the camera. So these are measures of how efficiently the system collects light, and this is a measure of how much light is incident. Typically, this factor and this factor is going to be somewhere in the range of 1, the ratio of the pixel pitch to lambda f number. The aperture of the camera and the range from the camera to the scatter, this is going to be much less than 1. In the case of the telescope that was shown earlier, this is a factor of around 1 over 400. But now the number of photons we can collect can be obviously much greater than 400, even though we take the square root of that. If we collect somewhere in the range of 1 million photons, we could expect this factor to be the increase in resolution to be on the scale of 100, and more generally could reach even scales of 1,000 or more. So this, what we've seen in today's discussion is that it's possible to reconstruct the field on remote scatterers and use that reconstructed field to image objects that are not directly observable from the camera. Now, in the case of the time-of-flight systems, the resolution is not extraordinary, but you are able to see things that are not directly observable. With the holographic technique, there's also the synthetic wavelength holographic technique. There's a loss of resolution associated with the synthetic wavelength, but at least you're able to cancel out the effect of the scatterer. If you are able to directly implement phase retrieval on the scatter, then you could use this to radically improve resolution on imaging the object, but this technique will be limited by the photon efficiency. Obviously, it's much less efficient to collect photons from scattered light than to collect photons that are directly emitted toward the camera. So these are techniques, though, that are very powerful and interesting because there's no real analog to them in geometric systems. They involve capture of the field itself. There is, however, a core assumption in what we've done, which is not accurate, and that's that the scatterer acts like a simple plane, phase modulation. More generally, of course, scatter and turbulence and path defects on the field are going to be three-dimensional, and they'll be more difficult to invert and control than simply modeled as a planar phase modulation. Next time, we're going to talk about how we can see through inhomogeneous media by characterizing the effect of the inhomogeneous media on the intermediate, on the field as it propagates through. What you're seeing here is imaging through multimode fibers by measuring the speckle pattern that comes out of the fiber. So we have a set of objects, and the objects on transmission through a multimode fiber generate a speckle pattern, but this group has trained a neural network to reconstruct the remote object from that speckle pattern, and we'll talk about how they did that in our next episode.